Pythagorean Theorem. So what is the theorem? The theorem basically says that in a right angle triangle, the square of the length of the hypotenuse is equal to the sum of the square of each of the lengths of the other two sides. Now, when you read this, it might not make much sense. So let's go through it step by step to understand what it's saying. So first, it says you need a right angle triangle. So here's our right angle triangle, and we're going to label it A, B, C. And A represents our right angle, which basically just means that it's 90 degrees. Now the next part of the theorem. It says the square of the length of the hypotenuse. Well, the hypotenuse is the side that is on the opposite side of the right angle. So our right angle is A, and to its opposite is line BC. So the length of BC, we have to square that. So we could write that out as BC squared. Okay, so far so good. Now what's the next part? Is equal. So BC squared is equal to something. So let's put an equal sign. Next, to the sum of. So to the sum of basically means that we're adding something. So BC squared is equal to something that's being added. Now the last part of the theorem states that the square of each of the lengths of the other two sides. Okay, so let's read this carefully. It says the square of each of the lengths of the other two sides. The lengths of the other two sides are represented by AB and AC. And again, we're squaring each of these sides. So we're going to end up with AB squared and AC squared. And thus, the theorem basically means that BC squared is equal to AB squared plus AC squared. And this is what we want to prove today. So we'll write it up here for reference. But before we get into that, to understand the proof that we're about to do, you need to understand the properties of similar triangles, because the proof we want to use uses similar triangle properties. So we have our two similar triangles, X and Y. The first property of similar triangles is that all the angles are equal. So let's label each of the angles. We have P, Q, R, and then for triangle Y, we have T, U, V. Now, though I have told you that both these triangles are similar, let's place triangle Y on top of triangle X to confirm whether their angles actually are equal. So first, let's see if P and T are equal. And as you can see, angle P and angle T fall on top of each other perfectly, so that means they're equal. Next, let's try Q and U. Again, they fall on top of each other perfectly, meaning that they're equal. And lastly, we're left with angle V and angle R. And of course, they fell on top of each other, showing that all three angles in both these triangles are equal. So we can write out that triangle PQR is similar to triangle TUV. One interesting thing about triangles is that all their angles add up to 180. So in triangle X, P plus Q plus R gives you 180 degrees, and in triangle Y, T plus U plus V gives you 180 degrees. So if you notice, the moment when we showed that P is equal to T and Q is equal to U, then automatically R must be equal to V. And knowing this is very convenient, because then in the beginning when we showed that angle P was equal to angle T and angle Q was equal to angle U, we can automatically jump to this step and say that two triangles are equal, instead of going to the third step and saying that angle R is equal to angle V, because it is assumed that they must be equal since the first two angles were equal. And this is known as the angle-angle criterion for similar triangles, and it's usually written shorthand as AA. Now, the second property that we're going to need is all the sides of the similar triangles are proportional, which means that the corresponding sides can be written as ratios to one another that equal each other. So for example, we're going to start with the big triangle and write the ratios of the lengths of triangle X versus triangle Y. And we'll get PQ over TU is equal to QR over UV, which is equal to PR over TV. Again, both these concepts we're going to need later on when we start our proof. So now back to our proof. And what were we trying to prove? That BC squared is equal to AB squared plus AC squared. So the first thing I'm going to do is draw a straight line, a perpendicular line that is, from A and label that point D. Now if you notice, when I did this, I ended up with two smaller triangles. And both of these are also right angle triangles because D is a perpendicular line. So let's first focus on triangle 1 at the moment and label it accordingly, and forget about triangle 2 for now. Now, we want to show that ADC is similar to ABC, and this may not be apparent at first, but let's flip and rotate this triangle to see which angles are similar and which are not. So if I flip it, notice that the label is flipped, and now I'm going to rotate it. Now the triangles look much more similar, but just saying that they look similar doesn't prove that they're similar. So first thing we need to do is, since we said earlier that because AD is a perpendicular line, that means angle D must be 90 degrees. And we also know that angle BAC in the green triangle is 90 degrees. So those two triangles are equal, meaning that they're similar. And since angle C in the green triangle here is the same angle C here, then obviously they are equal. So again, by angle-angle criterion, we have that triangle ABC and triangle DAC are similar. And we can write our formulae as shown. Next thing we want to do is we want to write out the proportions that we got of the two triangles because they're similar. So I'm going to start off with the sides of the green triangle versus the purple triangle. You can do this the other way around and still end up with the same result, but it's important to stay consistent. So first, we're going to have AB over DA is equal to AC over DC, which is equal to BC over AC. So we could just leave the proportion as is, but we need to notice that we may not need all of this proportion. And to know which part of it we don't need is by looking for which part of the proportion has the line AD in it. If you remember, we're trying to find a relationship between the sides of the right angle triangle. And so side AD was created by ourselves, and it's not really associated with the triangle we had originally. Thus, anything that has AD or DA, we can get rid of. And then that leaves us with the rest of the proportion. With this part of the proportion, you can now do the next step of the proof, which is cross multiply. So when you cross multiply, you end up with AC squared is equal to BC times DC. Okay, so that's everything we can get from the purple triangle. Now let's bring back triangle 2. So again, we're going to do the same thing with triangle 2. First, we're going to label it, then flip it, and rotate it. So its orientation is similar to triangle ABC. Now again, we want to prove that ABC is similar to DBA. So angle D is again 90 degrees, just like angle A of the green triangle. And in this time, we have this angle B, which is the exact same angle B over here. So since these two angles are common, and these two angles are 90 degrees, by the angle-angle criterion, we know that triangle ABC is similar to DBA. Again, we can write it out formally as shown. And this time we're going to write out our proportions the same way as we did before. So we'll end up with AB over DB is equal to AC over DA is equal to BC over BA. Again, we're going to cross out the part of the proportion that has a DA or AD in it, since that's the line that we actually added ourselves. And that leaves us with these two parts of the proportion, and we'll cross multiply. Notice that when we cross multiply, we have an AB here and a BA here. These are actually the exact same thing, it's just a different way to represent the same line. So when we cross multiply, we're going to end up with AB squared is equal to DB times BC. Now we finally have the two equations we need to do our proof. So let's write them out over here. And at this point you may get stuck what we should do first. Well, let's look back at what we were trying to prove at the top, the black box. So we were trying to prove that BC squared is equal to AB squared plus AC squared. And then when we look at what we ended up with, we have an AC squared over here and a AB squared over here. And according to our black box, we're trying to add these two. So let's try adding these two equations and see what we end up with. When we add it, on one side of the equal sign we end up with AC squared plus AB squared is equal to BC times DC plus DB times A of BC. And if you look closely on the other side of the equation, the first half has a BC in it and the second half has a BC in it. So using factoring, we can take the BC out as the common factor, and we're left with BC multiplied into DC plus DB. Now, if you notice, going back to our triangle, DC is this line right here, and DB is this line right here. So these together, when added, will give you the line BC. So we can simplify this and write BC times BC. And a simpler way of writing that is BC squared. So notice we have reached the final step of our proof, and this gives us AC squared plus AB squared equals BC squared, which actually matches up with what we wanted to prove right here. The only difference is that the BC appeared on this side of equal sign, and here the BC ended up on this side of equal sign. But that, of course, is the exact same thing. And thus we have proven Pythagorean theorem using similar triangles. If you'd like a written out explanation of this proof, just click on the link in the description and it will take you to a document where everything is written out, thus you can print out and use to your own benefit. Thank you for watching. I hope this helped you.